tutorials and these small short courses were done, and they are very helpful. So, and as per my part, I'm planning to give some highlight on the electronic schooling and the heat transport at the micro scale. And like out of it, like we will try to see that what is its role in basically minimizing the energy demand. So that basically lessen the load on the conventional energy production techniques, and that can basically lead towards the sustainable development. So the most of the focus of my talk is towards the electronic schooling, and then how we can make more efficient electronic schooling. So moving forward, I don't know, like if I need to introduce, because maybe the people don't know about me. So I'm Dr. Afzal Hussain, and I did my master's from Ali Muslim University, and then after I did my PhD from in South Korea at Inha University in thermofluids, and then after I worked there for 2.5 years, and after that I joined in Oman, Sultan Qaboos University, and after that, since then I'm there. So I'm taking the thermofluid courses mostly, and mostly like the related to heat transfer, fluid flow, and then some renewable energy concepts. Okay, so regarding the data centers, as we all know, like the demand of the data centers and the capacity is increasing every day, every passing day, and the data center is one of the major source of consumption of energy, and then we need to minimize that consumption. So what are the factors that affect the energy consumption in the data center? And so the heat generated in the chip, and chip is basically the processor, and in that processor, that heat needs to be removed. So how can we remove that heat from the chip surface to some outside environment? So that is an entire process, and in that process, there are different ways of doing that. Like if it's just a small desktop computer, so that it is basically releasing the heat in the surrounding environment, which is our room. So that basically giving an additional load to our AC system, our domestic AC system. And when we combine these multiple desktops, then it comes to the laboratory. And then in that laboratory or any computing facility, that heat load becomes more and more, and then we need more and more capacity air conditioning system for that. So in data centers, when we have the hundreds of these computers, hundreds and thousands of computers that put together, and then they put on the racks, and then we need to remove the heat from the chip surface, because that is generated at the chip surface. So there is a system of removing that heat, and so that system is basically need to be make more efficient. And when we make it more efficient, and that way we can basically reduce the energy demand. So if we look at that, what is the progress over the time that this microchip is having the number of transistors, and that each transistor junction that is basically producing the heat. So this number of transistors getting doubled like every passing 2 years. So, and this trend is continued until today, like more or less with slight deviation. So before we have like some processor, and then it comes to the more technology like Pentium, and then now we have the advanced version of this. So what is the heat generation at the chip surface? So if we look at this, the chip size is just 1 centimeter square, and at that chip size, the heat generation, if you look at that, the wattage of the thermal, and then it's a very high wattage, like the 100, 200, 300, something like that. So the flux is very high, and if you compare the flux generated at the chip surface, so it's like approaching the nuclear reaction process. The only advantage here, or only the thing that we are able to manage is that the chip surface area is small because the electronics is highly compacted. So the surface area is small, so the overall the heat generated, the energy generated at the chip surface is not the huge, but the flux is very high, and that we need to remove from the chip surface. And unless we remove it, that the electronics will not work. So to keep the electronics at the working temperature, so there are some standards, and then based on that, we can say that around 85 degree, that is for your commercial electronics, and then for military electronics, it may go a little higher. So that is the temperature that the chip should maintain. So there are different techniques to maintaining the chip temperature, or basically removing the flux generated at the chip surface. So initially, when there were not much integration in the chip, then we could have, able to remove the heat from the chip surface through the air cooling techniques. And then it comes to like the cold plate techniques, and then it comes to the the forced convection techniques. And then the more recent the research trend is that using the spray cooling, using the jet cooling, using some high basically the enhanced heat transfer fluids, and so on. So this way, this is the one way that we can remove the higher and higher heat flux from the chip surface. The other way is that how can we make it more efficient? So in that, we need to understand that what are the basically the components, and how we can do this thing. So if you look at the chip, the size of this module, that is your processor. If you look from the top, it is 1 inch by 1 inch, and then when you remove the cap of it, then the original chip, that is basically the silicon chip, is just 1 centimeter by 1 centimeter. So, and this is basically producing a very high heat flux, depending upon the wattage and depending upon the processor. So how can we cool this chip? So the one way of cooling this chip is that you put a heat spreader over it, that can be your cold plate, and then you can make the liquid flow over through this spreader, and that can take the heat away. So that is one of the way cooling this chip. So, and this is the procedure, like you can put a heat spreader at the chip surface, and then you can flow any coolant through the channels of that cold plate, and that can transfer the heat from the chip surface to any surrounding environment through your radiator and pump and reservoir arrangement. So this is like the kind of the add-on when you need when you want to cool it. So the other way is that you can make an integrated arrangement of cooling the chip, and that can be done when you basically make the surface of the chip cooled without having any add-on on it. So the chip surface is basically grouped, and the chip is you can imagine like it's 1 centimeter by 1 centimeter chip, and then when you are making groups on it through the micro machining, and then you are basically creating some channels having the dimensions like 100 to 100 micron, and then you are basically flowing the coolant over these channels, and then the coolant is taking the heat away from the channels, and then that coolant can be taken to any other place where you can comfortably release the heat. So we need some components for this also, like we need the pump, we need the filters, we need the heat radiators. So in this, there are a lot of advancement has already been done, and so normally like when we were not doing these cooling at the micro scale, we have the cooling at the conventional scale. So at the conventional scale, we already have developed several passive enhancement techniques. So the passive enhancement techniques is like changing the geometry of the channel or any fluid carrying passage, so that it can have you can maximize the area, and you can basically minimize the flow resistance. So the one way that the purpose is that you want to maximize the surface area, contact area of the coolant, and the other way that you want to minimize the flow resistance pressure drop. So this is a trade-off that we need for a proper design of the cooling channels. So the lot of research has already been done, starting from the simple parallel channels and then some different shapes of channels, that is triangular, trapezoidal, and there are some other enhancement techniques when you put any impediment or any obstruction in the flow, so that basically create a small local chaos in the fluid, and that chaos enhances the heat transfer rate locally. So if this keeps continue, then overall you can basically enhance the rate of heat transfer, and the heat transfer coefficient in that area is increased, so that basically enhance the overall heat transfer process. But at the same time, we need to take care of that the pressure drop should not go should not basically the escalate. So we need to control of the two things, that we want to maximize the heat transfer as well as we want to keep control on the pressure drop and the pumping power. Because when we do it at the micro scale, so we have to keep an eye on that what are the current state of the art micro scale pumps that can be integrated with this system. So the current state of micro pumps, we need to have an eye on that the what pressure and what flow rate these pumps are producing, and at the same time we have to check that what kind of the micro machining state of the art micro machinings available, so that can be used to fabricate the kind of the channels and the kind of the passive structures we want in the channel. So from the parallel they started, and then they moved to different shapes and then the different passive structures in the micro channel. And then so these are the few examples that we have the channels with the wavy walls, and then we have the channels with the with this ribs, rectangular ribs, and then we have the trapezoidal channels, and then and so on. So the one of the another constraint in the chip is that the temperature of the chip throughout the surface of the chip, it should remain uniform ideally. So what happens when we are having the channels grouped on the chip surface? So if this is the case, then what happens when the coolant enters from one end and then leaves at the other end, then obviously that when the coolant is entering into the channel, then it has a maximum temperature difference for the heat transfer to take place. So in the near the entrance, the higher rate is achieved, and at the exit the lower rate, and at the same time at the near the entrance the chip surface is less, and at the exit the chip surface is high. So that makes a temperature gradient at the chip surface, and that is another detrimental factor for the chip life and durability. So that we want to overcome. So how can we overcome that? So for that purpose, like instead of making the inlet and outlet laterally, so that and that generate basically the temperature gradient in the direction of the flow. So to avoid that or to minimize that temperature gradient, what we can do, that we can make a multiple impingement of the fluid, a kind of spray, a kind of jet on the chip surface, and that can basically reduce the non-uniformity of the chip surface. So for that purpose, let's say that this is your rectangular chip, and then these black dots is basically the micro jets that's striking on the chip surface, and then the chip surface is getting cooled. So this way we can minimize the temperature gradient to some extent. So it depends upon that as you increase the number of these impingement, the jets, so your temperature gradient will be further reduced. So this was proposed, and it was successful to minimizing the temperature gradient, and as well as like if there is any local heating, so that can also be minimized through this. So further, There are different other designs like what can be further make it more efficient. So when the jets are striking in the channel and the fluid is flowing, so the different sort of arrangements were sought and researched, like can we change the jet diameter? So when while changing the jet diameter, so what can be the possibility, like either you can make the uniform diameter or you can change it in the direction of the flow, either you increase in the direction of the flow or you decrease in the direction of the flow. So that combination is sought, that what can be the best combination and what can be the best diameter. So these were the things that need to be optimized. So they did it, and then successfully they can minimize the temperature gradient. The another way of doing is that when the chip is hot and then you want to cool it, you strike the fluid jet on the chip surface from one nozzle, and from the other hole you can suck the fluid that is spread over the chip. So basically the cold fluid is striking and the warm fluid you sucked, and then that can be taken to other place. So this is another way of cooling the chip. So that was also tested, and it is also a successful technology. But still, like, these are in the experimental phase. Like in the commercial product, especially at the micro scale, this has not been realized. Although it is the mini scale, like in the size of millimeters, they have been proved. So we have different combinations and uh, the different arrangement of the jets. So it depends upon like which combination and which arrangement can give you the minimum of the flow resistance and the maximum of the rate of heat transfer. So that combination can work for basically the energy efficient system. So I'm not going into that detail that what are the results. So the results can be seen like through the when you go through the research papers. So this is another technique that when we have the jets are striking on the chip surface, and while the jet fluid is going towards the outlet, it is finding a obstruction in the middle of the path, and that obstruction is basically further creating a chaos, and that enhancing the heat transfer coefficient and the rate of heat transfer on the way. So it is basically a kind of a hybrid process, that the one is the jet and then we have the passive enhancement, and that is happening in a micro channel. So it is basically having the three effect. The micro channel itself is uh, good for the heat transfer process, and then we have the jets, and then we have this micro pillars. So different arrangements, like we have the small jets. So small jets are striking on the chip surface, and the big one is extracting the fluid. And the other way, that the big one is striking the fluid on the chip surface and the smaller one is extracting the fluid. And then we can basically model it and find out that the which combination is working well for our purpose, that is to minimize the temperature and to minimize the temperature gradient. So we can solve this, and we can do this through the experiment, and we can do this through the numerical methodology. But obviously the doing the experiment is much tedious in case of when you do with the micro scale fabrication, and then the micro scale instrumentation, and the micro scale experimental setups. That's a very tedious job. So most of the time that the people do it at the mini scale instead of designing a micro scale experimental setup. They opt for doing it at a mini scale. So, and then they basically both are working on the continuum regime. So the continuum fluid fluid mechanics is applicable to both. So so whatever you are getting at the mini scale, so that can be extrapolated to micro scale. So these are the flow structures, like when we are doing the flow in a channel, and then the fluid is flowing over the chip surface. So in the beginning we see that the temperature is less, and then at the near the outlet we see that the temperature is higher. So this temperature gradient is unwanted for the chip surface, so we need to minimize that. And here the cross section of the flow. So the fluid is flowing, like the flow is flowing inside the slide. So these are the velocity profiles and the temperature profiles. So we see that the temperature of the substrate at the bottom is higher, and at the top it is less. So here also it is giving us a temperature gradient, so which is again is unwanted. So with the different arrangements and different designs, we want to minimize it. And these are the different some representative designs that are used in the past through different researchers, and including some of my colleague researchers. So when we make the jet impinged on the chip surface and we strike the jet on the chip surface, so this is what is happening. Like here we are entering the fluid which is at low temperature, the coolant, and as it passes over the chip surface, and we see that there is a significant increase. So the increase in both that, the increase in the temperature of the fluid and increase in the temperature of the surface and increase in the velocity also, because all the fluid is accumulating here. So here we have this temperature distribution for the jet case. So where the jet is striking, then the temperature is less, and the surrounding, the temperature is increasing radially. So again, we need to make a proper a combination that how far a jet could be, and then what should be the pitch and what should be the diameter of the jet, and to keep the temperature in the desired state. So these are again the flow structures in the same line, that when the jet is striking on the surface, and then we see that what combination and what diameter of the jet can give us the best possible results in terms of minimizing the temperature and maximizing the rate of heat transfer, especially the heat transfer coefficient and Nusselt number, and minimizing the flow resistance, the pressure drop, and the pumping power required. So here we have the one of the that what is happening with the flow when the jet is coming from this nozzle, and then the fluid is moving, and then there is a passive structure which is a pillar here, and then what is happening with the fluid molecules. So we have seen the comparison of different combination, that it can be a simple parallel channel, it can be a channel with some passive structures, it can be a simple jet, it can be a jet with pillars. So with all these combinations, so the hybrid combination that we have, and that is including the jet in microchannel with the pillar, is basically giving us the minimum thermal resistance. And so with that is good for the from the viewpoint of the minimizing the temperature and minimizing the thermal resistance. But at the same time, we have to keep an eye on the pumping power, that what pumping power it is using basically. So that is the constraint that comes from the state of the art, the pumping technology existing. And then again, like we can see, like because the fluid is moving along the length of the channel, so what will happen if you incline the jet? So does it make any difference in the rate of heat transfer, and what will be the effect on the pressure drop? So that kind of a study also been done, and then we saw that it can enhance the heat transfer capacities, but at the same time the flow resistance, the pressure drop is significantly high. So again, like we need to model it through different parameters by changing the jet diameter, changing the jet angle, and changing the and finding the best combination for that. So the more recently we introduced the porous material, because it's not easy to have a porous material in the microstructure. So So experimentally it is much difficult to do the experiment, but the modeling we can do, and through the modeling we can get some idea that what we are going to have when we do the experiment. So here there are different combinations. That this is the empty channel, this is, there is no porous inside, and there is only the fluid coming and the striking on the chip surface. And then here if you fill this with the porous material, and then here that you fill to some extent with the porous material at the base, and here you are filling it to some extent on the side of the channel wall, and then here you are basically providing the porous material in the direction of the flow. So the different combinations we basically uh, modeled, and then find that what is happening, and which combination is giving us the more efficient result. So again, that there is a lot of trade-off, that when you want to try, when you want to reduce the temperature and when you want to increase the heat transfer coefficient, then it is at the expense of pressure drop and pumping power. So we have to make a trade-off, like what is the pumping power that we can basically bear, and then to what extent that we want to minimize the thermal resistance. So here we can see that the different combinations, they're giving the different results. And as I said, like it depends upon the trade-off, that the some combination, what combination can be best fit in your requirement. So these are the recent advanced in the micro scale heat transfer and electronics cooling. So, and there are a lot of results that I don't want to present, because that will lead to more like insight into the research, so that may not be good for the common audience. So this is it. And if you have like if you any questions, and if anything you need more clarification regarding this, then I will be happy to answer your queries. Thank you very much.
Sir, there are two people, Anand Tembulkar and Rajat Haider. They have raised hand. Just one by one, ask your questions.
Sir, I want to say thank you only.
Yeah. What about Raja Haider?
You're welcome.
Raja Haider? Shambhu Prasad Meher, SP Meher Saab?
So here I want to add that what is the nature of the coolant, or what type of coolant is used?
When we it depends, like initially uh, it was the air cooling, and then when we go for the constrained channel flow, then it was in liquid phase. So it was proposed that the filtered water can be used, and then it was proposed that any kind of a refrigerant be used, as long as like it's not toxic and it's not harmful, and as long as it is not basically having the ions in it, because it's flowing inside the electronics.
Yes. So whether we can use hydrogen cooling also? Hydrogen cooling?
Hydrogen cooling. Hydrogen cooling, yeah, as long as it is like a hydrogen molecule, not the ion. Yeah.
Yes. Okay, sir. Thank you, sir.
Welcome.
Yes, any other questions?
Sir, I have one question.
Yeah, welcome.
Sir, we know that heat pipe is also used for cooling, electronics cooling. So, have you done, sir, some analysis or comparison with the heat pipe?
Yeah, what I presented is like more of a single phase cooling. So when we go for the heat pipe, it's a phase change, and we have the concept of the porous material as well. So in this presentation especially, I did not include that phase change. but there is some work I have not done much in towards the phase change cooling, the one or two projects I did, but that I have not included here. So at the micro scale, the phase change is it gives us very good results. And as we know, the latent heat can be taken from the surface, while the surface temperature can be kept constant. So that was the advantage with the the phase change cooling, and that's very promising. Basically, it's not not part of my presentation today, but it is definitely a very promising method.
Okay, okay, thank you, sir.
Dinesh sir. So now I think no more questions. We thank
Thank you very much.
Yeah, we thank Professor Afzal for his very last moment attempt, very short notice because of Professor Ashish Shukla could not be contacted at last moment. So these are some problems we faced during